Welcome, everyone. Let's get started on an exciting journey into the core of Apache Spark's advanced data handling capabilities. Welcome to our deep dive into Apache Spark's complex data types. Let's look at the first bullet point. What exactly are they? Simply put, complex type structs, arrays, and maps allow us to store nested, hierarchical data inside a single data frame column. Moving to the basics, while a primitive type holds just one piece of information, a complex type can hold lists, dictionaries, or even whole nested records. Why is this so crucial for us? Because modern big data formats, like JSON or Parquet, are highly nested by default. We need a way to process them without losing that valuable structure. How does Spark handle this? It uses its Catalyst optimizer to query these nested fields natively. Now, for a quick deep dive, in traditional relational databases, you'd normalize data and use joins. In distributed computing, joins are expensive because they shuffle data across the network. Complex types keep related data physically together on the same node, significantly boosting query performance by avoiding those heavy shuffles. Looking at the diagram on your screen, we can visualize this concept simply. At the very top, we have a standard Spark data frame column. Notice how it branches into two distinct categories, primitive types on the left and complex types on the right. When we follow the complex types path, it further divides into the three core structures we will master today: struct type, array type, and map type. Finally, observe the dashed arrows pointing down to nested hierarchies. This illustrates that these three types aren't just isolated tools. They combine and interlock to represent incredibly deep, complex data models naturally. This flowchart is your roadmap for today's training. Let's zoom in on our first complex type, the struct type. As our definition states, a struct type is essentially a record. Think of it as embedding a miniature row right inside your data frame column. It has a fixed number of named fields. Looking at the basics, we construct a struct type using an array of struct field objects. Every struct field defines a name, a specific data type, and whether it allows null values. Why do we use structs? They are perfect for grouping related, heterogeneous attributes. For instance, instead of having separate columns for street, city, and zip code, you bundle them into a single address struct. How do you query this? It's incredibly user-friendly. You just use dot notation, like address.city. Our deep dive here is fascinating. When Spark writes a struct to a Parquet file, it physically stores each nested field in its own columnar format. If your query only asks for address.city, Spark's column pruning skips the rest of the address entirely, saving massive amounts of disk I/O. Let's walk through this specific structure visually. On the left, we have our main struct type, representing an address. Notice how it breaks out into three specific, named struct fields: street as a string, city as a string, and zip code as an integer. This perfectly illustrates how a struct can hold mixed data types under one umbrella. On the far right, the diagram highlights how we actually extract the data we want. The arrow points from the city field directly to our query mechanism, the dot notation. By typing address.city, Spark knows exactly how to navigate this internal structure and pull out precisely the data you requested without touching the rest. Moving on to our next structure, the array type. By definition, an array type is a collection of elements where every single item must be of the exact same data type. Let's look at the basics. Unlike structs, which have a fixed number of fields, an array allows a dynamic number of elements per row. One user might have no items in their array, while another has 100. Why is this useful? It allows us to seamlessly model one-to-many relationships natively. Imagine a user with multiple phone numbers or a list of recent purchase amounts. How do we manipulate them? Spark provides a rich set of built-in functions. You can check the length with size, check for specific items with array contains, or flatten the array. In our deep dive, consider the alternative. If we didn't have arrays, we'd have to flatten the table, repeating the user's name and ID on a new row for every single phone number. Arrays prevent this massive data duplication, keeping your data dense and your memory footprint low. This visual demonstrates the power of the array type. At the top, we have a single logical customer row. It contains a standard string field for the customer's name, but next to it is the phone numbers column, defined as an array type. See how this single column branches out to hold multiple distinct phone number elements. All these elements belong to that one single customer row. In a traditional database, you would need a completely separate phone numbers table and a join operation to achieve this. Here, the list of numbers lives directly inside the user's record, tightly bundled together for optimal access and retrieval speeds. Now let's tackle the map type. As you can see from the definition, a map type is an unordered collection of key-value pairs. If you code in Python, think of it as a dictionary. Looking at the basics, a map type requires you to define a data type for the keys and a data type for the values. For example, your keys might be strings and your values might be integers. Why do we need maps when we have structs? Maps are built for sparse, highly dynamic data. If you have product attributes where one product has a color and size, but another has voltage and wattage, a struct would be too rigid. A map handles this perfectly. How do you query it? Just pass the key in brackets, like properties color. Our deep dive reveals a critical architectural detail. Spark doesn't index map keys for O1 constant time lookups. It iterates through them. Therefore, maps are incredibly valuable for ingesting schemaless, flexible data, rather than being used as high-speed lookup tables within your queries. Let's explore the map type via this diagram. On the left is our map column, named Attributes. Notice how it holds multiple, distinct key-value pairings. One row might have color mapped to red and size mapped to large, while another row might hold voltage mapped to 110V. This highlights the sheer flexibility of maps. The schema doesn't care exactly what the string keys are, as long as the types match. The dashed line at the bottom shows our query execution. By asking Spark for the key color inside the brackets, the engine scans the map and extracts the value red. It is simple, elegant, and incredibly flexible for unpredictable datasets. Now we reach the truly powerful part, nesting complex types. What does this mean? Spark allows you to place complex types inside of other complex types, up to 100 levels deep. Let's look at the basics. The absolute most common pattern you will see in big data is an array of structs. Imagine a list where every item in the list is a detailed record. It's like having an entire mini-table embedded inside a single cell of your data frame. Why do we do this? Because this perfectly mirrors real-world API payloads. Think of a digital shopping cart, one user, containing an array of highly detailed item objects. How is this set up? You programmatically build your schema by nesting a struct type inside an array type definition. Our deep dive brings us back to performance. Why not use two tables? Because if you join a user table and an items table, Spark has to shuffle massive amounts of data across the network to match them up. By nesting the data, Spark guarantees that the user and all their items live in the exact same physical storage block. Zero network shuffle required. This diagram brilliantly illustrates the array of structs concept. At the top, we have a single order row. It has a primitive order ID, but next to it is the items array. As we follow the arrows down, the array doesn't just hold simple strings, it holds complete structs. Item 1 and Item 2 are complete subrecords, each branching out to have their own product ID and price fields. This hierarchical layout perfectly captures the reality of transactional data. When Spark reads this one-order row, it instantly loads all the associated product IDs and prices directly into memory on a single executor, completely bypassing the need for expensive network joins. So, we know how to store nested data, but how do we analyze it? Let's talk about transforming complex types. What do we do when our BI tools need flat data? Spark provides specialized functions to unnest hierarchies. Looking at the basics, the most critical function is explode. When you apply explode to an array or a map, Spark takes that single row and replicates it, generating a brand new row for every element inside the collection. Why is this necessary? Because while nested data is phenomenal for fast storage and ingestion, downstream systems like Tableau or machine learning models expect flat, two-dimensional tables. How do we do it? We literally write explode call array name, which creates our new rows. Then we extract the fields using the dot notation we learned earlier. But be careful. This brings us to our deep dive. Explode causes a row explosion. If an array has 100 items, one row instantly becomes 100 rows in memory. To optimize performance, always try to use Spark's higher-order functions to filter out unwanted array elements before you apply the explode function. This visual elegantly displays the mechanics of the explode function. On the left side, we have our densely packed data. Row 1 contains an array holding two items, A and B. Row 2 contains an array with just item C. When we pass this data through the explode operation, watch what happens to the output on the right. Row 1 physically splits into two distinct rows, row 1A for item A and row 1B for item B. Row 2 simply maps to row 2A for item C. We went from 2 rows of input to 3 rows of output. This flattens the hierarchy, making it instantly compatible with standard SQL aggregations and grouping operations. Let's ground all this theory in a real-time use case, e-commerce order analytics. Imagine the scenario. Our platform streams 10,000 JSON order events per second. Every JSON holds a customer ID and an array of item records. Our challenge: the business needs a real-time dashboard showing total revenue per customer, but the item prices are trapped deep inside those nested arrays. How do we solve this? First, we define an explicit nested schema, a struct containing an array of structs. We enforce this schema as Spark reads the streaming data. For execution, we take that data frame, use explode on the items array so every item gets its own row, extract the item.price using dot notation, and then run a simple group by and sum on the customer ID. Now for the deep dive value. Why is this architecture vastly superior? First, providing the schema explicitly stops Spark from doing a slow, full dataset scan to guess data types. Second, by processing the nested array in place and aggregating it locally, we completely sidestep a multi-terabyte network shuffle. This is how you achieve real-time speed at massive scale. Let's track the data flow for our real-time use case. At the top left, the raw JSON event stream flows into Spark. We intercept it at node B using an explicit schema, creating our data frame with the nested arrays intact. Moving down, we hit the transformation phase. We explode the items array, which flattens our data, allowing us to seamlessly extract the item.price field. Finally, we push those flattened rows into our group by and sum aggregation engine, which directly feeds the real-time revenue dashboard. This pipeline is clean, linearly scalable, and avoids the traditional bottlenecks of distributed data joins. As we wrap up our session, let's lock in some critical best practices for performance tuning. First, always define your schemas explicitly using struct type. Do not use infer schema in production. It forces Spark to read the entire dataset just to guess the data types, completely destroying startup performance. Second, prune your data early. If you only need a nested city field, select address.city immediately so Spark ignores the rest of the file block. Third, avoid exploding data unless absolutely necessary. Row explosion eats up memory. Try to use Spark's higher-order array functions to aggregate data directly inside the array without flattening it. Finally, remember the golden rule: complex types are a performance tool. They guarantee that parent and child records are co-located on the same server, allowing you to avoid the dreaded shuffle phase of a distributed join. By mastering structs, arrays, and maps, you are now equipped to engineer top-tier, highly optimized big data pipelines. To truly master these concepts and crush your career goals, I invite you to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Thank you for learning with me today. Our final diagram is a quick contrast between bad habits and best practices. On the top left, using infer schema forces a full data scan, leading directly to slow performance. Below that, providing an explicit schema bypasses the scan for a lightning-fast startup. In the lower section, exploding every array can trigger out-of-memory errors due to row duplication. The better approach is using Spark's modern higher-order functions to process the arrays directly in place, keeping your memory usage low and your clusters healthy. Keep these visual rules in mind as you build your pipelines.